All right, so we're here in the second meeting of the ML in production interest group of ML Collective and Full Stack Deep Learning. And today we're talking about the second chapter of designing machine learning systems by Chip Wynn. So this chapter's title is Data Engineering Fundamentals, and it's really kind of like a high speed, high level, any percent speed run, if you will, of the ideas in the data engineering component of an ML system. And this chapter, it's if you have never encountered this material before, it's a super dense chapter. There's a ton of ideas here and lots of pointers to different places. But so that makes it, in some ways a challenging chapter, but it's also this sort of like kind of component of the stack that's really become almost like its own thing, this like data engineering discipline that's become more and more separate from the rest of ML engineering. Because as Chip says in the little blurb at the top, this is more about databases, and there are some differences in what you need from databases, what you need from data engineering for ML than what you might need for any data intensive application like a Facebook or an OpenSea or what have you. But there's actually, in the end, a lot of this, there's successful abstractions about data, about ways to read it, ways to write it, that can be ported fairly well to lots of things in machine learning. So what that means is that when you're designing your ML system, either this is going to be like your bread and butter in your wheelhouse and you're reading this chapter nodding along the entire time, or that person is on your team, or that team is partnering with you to build this system, and that so you don't need to know all of this in great detail. But it's worth being able, I think, to kind of like speak the language of the data engineering team if you're not on it. And so that's, I think, the main goal from this chapter. And one of the things that I got out of it as somebody who's not a data engineer. So I don't know if anybody in the call right now has data engineering experience and can speak to that at all.
So I quickly want to ask, what exactly is like data engineering? I mean, I figured that you kind of like explained it a little bit, but is it like data pre-processing or how the data is collected and stored or what?
Yeah, I would say that one way to think about it is if you have mostly done like model engineering, so to speak, if you've mostly been like like designing architectures and training models, then you consume, let's say, somebody has handed you either like tensors and RAM or maybe like, a PyTorch data loader or something like that,
Yeah.
and from that you produce your model. But you talk about your model as like, oh, my model learned to read human handwriting, or my model learned to caption images or whatever. And there's a giant gap between the real world and what you consume as data to go into your model to produce your final like model output. And that closing that gap is the job of the data engineering team in an ML team.
Okay, that's pretty interesting.
Yeah, that's maybe like a high level or a like intuitive definition. Maybe another way to tell is like the data engineering team are the people who manage all the databases and the like meta databases that tell you how all these things interact. Yeah, so I think the the strategy here, like if you're unfamiliar with this data engineering stuff and you want to learn it, and maybe you're coming from the like more model engineering part of the stack, my recommendation, this chapter is sort of like an advertisement or like a high level overview. And what you want to really understand that material in depth is this suggestion here, this designing data intensive application. It's an O'Reilly book that's like very, very, very much worth the price. This one here with the jumping boar on the front by Martin Kleppman. This is like the go-to text for learning about how like it's not like a college class textbook that teaches you databases. It's more of like how all of these pieces fit together to build an application that has software and data that interact with each other to produce the final result. So it gets referenced really repeatedly throughout chapter 2, and it's kind of like it's where almost everybody that I've talked to about data engineering, as I've been trying to learn more about it, has brought this book up when I ask them what they recommend to get more, where to learn more. Martin Kleppman is one of the people who worked on some of the like biggest database technologies in the last like 10 or 15 years. He's like embedded in the community and in like the open source community, and then he's also a professor, so like well poised position to write something like this. So it's very readable and very approachable. I actually have it on my desk right now. Here it is. Boom. The Jumping Boar. Great book. I highly recommend it.
Nice.
Great. Yeah. So at a high level, these are the like fundamental ideas or like core concepts, the like common buzzwords, maybe even that you'll hear when people talk about the data engineering component of an ML system. And so there's data formats. How do you organize your data? All the way down to the level of like, what does it look like on a disk? What do the like literal bytes look like on a disk? And like, what file format do you choose? And then how do you fundamentally data is not just bits by themselves, it's bits in relation to other bits. And so you need data models that relate one piece of data to another piece of data. So databases like sort of collect up all this data and know how it relates to each other in some way, whether that's with a what's called a relational model of data, which looks like a bunch of separate kind of tables or data frames that point to each other, or with it's one of these like NoSQL non-relational database models that have different ways of relating the contained data to each other. And then once you have your data formatted and your data organized, you have to think about how that data will be accessed, how will you be able to write and add to the data, and how will you be able to read from it. And the reason why this is all so complicated here, by the way, is that this is the like most performance sensitive and performance intensive part of almost like every major application. Like Twitter needs to ingest, I don't know, millions of characters a minute. It's really large quantity of characters per minute, and their speed at being able to ingest that, transform everybody's Twitter feed in response to the fact that that somebody has tweeted something. All their followers need to know about that. As their followers start retweeting it, it needs to go to other people. So this is like this is massive changes that could be viewed in a browser anywhere at the world, and people want it to happen in like milliseconds. They want to be like unable to notice the latency. So this is this like really performance critical, latency sensitive, high scale piece of an application. And so because of that, there's just tons and tons of optimization. So databases are designed with like specific facts about the hardware very closely in mind. With like there's databases for if you can fit everything in RAM versus if you can't fit everything in RAM. There's databases that are really good at holding on for data for a long time. There are databases that are better for reading and better databases that are better for writing. And I'm even like speaking at a very high level of generality relative to how specific people get, down to like very careful design of the data structures and memory access patterns at the core of the database. And so it's not just like, oh, I write a file and then I read a file, which you can put behind an abstraction barrier and ignore. It's much more complicated than that, and the complexity really quickly rises directly into your face as you're designing your system. So that's why these databases are thought of as these like data storage engines, as like an active process that reads data for you and writes data for you. And how that happens is tightly coupled with how you want to process the data. Do you want to pull out just one thing at a time, like just one customer at a time, so that you can update their shopping cart and then charge them money? Or do you want to pull all your customers all at once, and you want to just look at when was the last time they came into the app, so that you can make a feature that can be used to predict whether they're going to come back in the next week? So those differences are really, really important for the ML system. Like, which kinds of transformations is your ML system going to be applying? What kind of analysis will it be doing? And because these ideas have been around for a while, there's lots of acronyms, there's lots of terms, there's lots of like shared concepts in the data engineering community for understanding all of those things. And then that I think that kind of also covers, like at a high level, what I was describing also covers this like models of data flow section, which is that in your application, eventually you're going to have data moving around between, it's not just going to be stored in one single place and then you pull it from that one place and then maybe you put stuff back there. You're going to have more than one database. You're maybe going to have lots of services, like maybe you have a translation model and you have a toxicity detection model and you have a computer vision model for writing captions, and these are all living inside of your ML powered application, and data needs to move between them. And so there's these models or modes of data flow of how data might move between those things. And that's the last section there on modes of data flow. And that's a high level overview of this high level overview of the fundamentals of data engineering. So does any part of that sound particularly interesting to anybody? Does anybody want to dive in on a particular?
I'd be interested in hearing a lot more about extract, transform, and load. I hear a lot about it where I'm like studying for like interviews and stuff like that. So it'd be nice to add that to the stack.
Yeah, great. Any other suggestions for what to put on our reading stack?
I have a question. Do you know if this will talk about data security? So if I'm building something that needs to be shipped to a client and they're giving data, will this address security at all?
Let's see. This chapter, because it's just about the like fundamentals of data engineering, does not touch on security. Yeah, I think the expectation here, if you have that level of complexity of a data problem, you have a like data engineering specialist to handle it, to do things like anonymize the data or whatever.
Yeah, I'm just curious, just to be familiar with it. Of course, someone with an expertise in it would implement. Just out of my own familiarity, I want to have some basic understanding. That's kind of where I'm coming from.
Yeah, no, I think that's wise. Okay, well we'll jump to extract, transform, load. I'll head down there. If anybody's got anything else that they want to talk about, maybe drop it in the chat in the Google Meet. I'm going to actually recommend that we just take maybe 5 minutes to look at this section and just sort of like quietly read it to ourselves and then come back together. Just because it is such a big chapter, it's like 30 pages and dense. It's probably helpful to like refresh our memory on this to extract this section from the chapter and load it up into our RAM, so to speak. So I'm gonna go off camera and off microphone, and we'll read this section. So we've had 5 minutes to look over this section here on extract, transform, load, and extract, load, transform. Does anybody have any like immediate thoughts or questions about this section? Maybe Moise, since you suggested it, if you have anything to say.
Yeah, I think it's pretty interesting how this seems to be like a pretty common like thing that's like talked about when you're like studying for interviews and stuff like that. But it sounds like the scalability of it is like a little bit bad. There's this like one part where they say that like as like the amount of data grows, it becomes a bit inefficient to do this abstract load transform idea because it's like inefficient to like search through data and stuff like that. I also find some of the language to be really interesting. Like for example, they use data lakes a few times near the end. And also in this diagram they have over here, they talk about they have the word data mart and warehouse. And I'm not really familiar with, those things, neither a data lake. Does anybody know the definitions of these things or what they are intuitively off the top of their head?
Yeah, I can give an answer. I wanted to make sure if anybody else wants to take a crack at this, feel free.
So I kind of assume that like a data lake is like a large reservoir of data that you can like pull through or pull pull from at any time.
Yeah,
But I'm not
that's
exactly sure.
actually, yeah, that's pretty close. Let me go down to that diagram on my shared screen here that's got our extract transform load. So just to like get everybody on the same page, the idea here is you've got maybe lots of sources of data. So on this side we have a database. Maybe you're an e-commerce website. The classic database use case is for commerce, right? So I've got users that have things in their carts and that they want to like add something to their cart, they want to remove something from it. All that stuff goes into that database. Or maybe I'm a social media website and that's everybody's posts. That's all the images that people are posting, links to all the images that people are posting, all the text that they're posting, all this information goes into that database. Maybe like other parts of your app expose information. Maybe you're monitoring your application and it produces logs, and those are coming out of your app in the middle. Or you're pulling, that app could also be somebody else's data source, like you're pulling data from somebody who's running a data service. Or you could have just like a bunch of files stored in something like Amazon S3, like cloud file storage. So these are all possible sources of data. What we want to do is take those and get them into a format and a setting where they can be used by like machine learning, like used for machine learning purposes. So the classic view of this is like 15 years old, maybe, is the like data science view, which is lots of stuff is going on in your application. And like you wanna just like kind of do science on that. You want to know what's going on in it. You want to discover phenomena. You want to like produce like basically like papers and research about what's going on in your application. And that sort of style is what gave birth to the like big data. One of the things that gave birth to the like big data buzzword. And so you want to get that into a format where it's usable for machine learning. And I think one of the things that's most critical about that is like there are a couple things that you might want to do. One is, if you've just got all this like big old pile of files somewhere, then you want to turn that into something structured. So that connects to what Moise was saying about data lakes. A data lake is basically an unstructured gigantic collection of data. So your intuition was spot on there, that it's just like data that's not been really organized. And you want to organize that data so that your machine, like the machine learning team, can, knows which users uploaded which images, or knows like on what date the images were uploaded, or whatever. So you'll maybe take those flat files and turn them from a lake of unstructured data to a database of highly structured relational data. But you'll notice that there's like database on the left and database on the right here. A database can be a source of this and a target of it. And that's maybe confusing a little bit. Like why, what do you do if you're pulling them out of the database and then putting them back into a database? Like what's going on here? What's the transformation? And I think the core bit here is that this database, if it's, like the eBay e-commerce example or the social media example, that database is like, that's running your application right now, right? That's like the core piece. One of the core pieces of your application is this database full of information about like what users are doing, so that your app can know what they're allowed to do next, or whatever, or report that information to other users in the case of social media. That thing is like that's the engine of your application. And you don't want your machine learning team just like pounding that database with queries, being like, what are users doing now? Has anybody checked out this thing? Like if I filter by users who were here today, do I like, how many of them were here yesterday? Those kinds of like analytics queries are expensive. And if they were allowed to happen at the same time as what users were doing to interact with the application, you could have really serious like outages, right? Like your machine learning team decides to run, or your data science or machine learning team decides to run some big query at the same time as like, Kim Kardashian's new photo breaks the internet or whatever. And then you're in trouble. And so you want to separate these two things. And that's one thing that these like extract, transform, load pipelines do. Create a barrier in between data that the machine learning team sees, like the like computers, the like physical infrastructure on which that's running, and the like databases that you interact with, to get to that data, and the like databases and physical infrastructure that supports the actual application. So there's like lots of things tied up in this concept of extract, transform, load, or extract, load, transform in these like, which is why I think it comes up so often in interviews when people are talking about data engineering, because it ends up at the interface, for example, at the interface between your application team and your like user experience and the machine learning team and the data science team. Any questions on that front? There's more vocab that we can go over, data warehouses, data marts, but any questions so far?
So on the left side, you would call that a lake, and the right side would be more structured warehouse.
Sorry, specifically this thing here of flat file of here, where like you're imagining just like a big collection of like JPEGs, right? Like to first approximation, every image uploaded to Facebook's ML team wants to use for machine learning. So those, I don't know how it's structured, but let's just say those are all just sitting on the cloud somewhere, stored on Amazon, stored on Google Cloud, whatever. That if it's like basically unstructured, maybe small bits of it are kind of structured, like every user, like a particular, everything that happened in one day is maybe in one folder or something, but it's not like rigorously structured. That is the sort of thing that people refer to with data lakes. So that's one type of potential source, just like a database is one type of potential target for one of these processes.
Okay, got it. Thanks.
Yeah, there's a lot, because the problems are fairly complex and because the stakes are really high. There's a lot of very bespoke specific solutions, and so there's like a proliferation of vocabulary here, and without direct experience with these like specific situations, it can be really hard to keep all of it straight, lakes and databases and so on.
Could you briefly describe each one of the targets?
Yeah, let's dive into that. So a data warehouse, actually one nice source for this I found, obviously the Designing Data Intensive Applications book, the Kleppman book is really good for it, but if we just go wiki data warehouse, if I remember right, there's a really nice picture on, actually it might even be on the data mart page. Data lakes, databases, data warehouses, data lake houses, and data marts. It's really a lot. Okay, so
That's amazing.
it's really a lot. It's very upsetting. So
a marketing person made this.
Yeah, it's
There's
hard.
no way.
So people really do use these terms and think about them when they're designing these kinds of systems. Like, maybe they won't use every single vocab term here. Maybe that's a little bit more marketing-y. But people do think about these things as like discrete units with arrows between them of different kinds of jobs. So, because otherwise it's just like, if you don't put this kind of like structured discipline on your system, everything just becomes like a big spaghetti pile of like interrelated things with undeclared dependencies and just tons of breakage. So, well, yeah, I totally get that this might remind people of the least interesting PowerPoint they've ever seen in their life, but these system diagrams are helpful.
Yeah, I agree.
But okay, so we'll put these two parts here, operational systems and integration layer, together. This is like our sources side here for what we were talking about so far. So like operational systems, that's what's actually happening. Marketing, sale, like that's our application doing stuff. Maybe external data, right? We talked about that as well. That all needs to get pulled in. And then the idea of a data warehouse is that this is the one-stop shop for everybody within the organization who wants to know about data in order to like make this, like, they aren't operational, like they aren't doing the direct selling, or they aren't like running a marketing campaign, they aren't running the like Twitter feed. All that stuff goes off of the operational systems component. The data warehouse is for everybody internally who's using data to drive like either machine learning applications or like human decision making. So humans want to query how the marketing campaign is going or how things have been selling, and you don't want them having to go all the way down to the operational system to get that information. So you extract, transform, load all of stuff from here into a data warehouse. So this is just like you might have all of the like products that you're selling in a warehouse in your company. You put all of the data that you need in the data warehouse at your company, and then people can go there as like a one-stop shop.
Is it correct to say the warehouse here is the same as a data lake?
I would say warehouses. The difference is that warehouses are structured usually. Like warehouses have,
okay.
yeah. So like you wouldn't call a data lake like in the platonic ideal of these things. The data lake is completely unstructured. It's like dropping into somebody's file system.
External data on this chart.
External data would be the one most likely to be like
Okay.
a complete lake in this chart. Yeah. Yeah. So then, and then data warehouses are like highly structured, right? You have like very clear ideas of where everything is, and it like this is the place where you would find them like highly structured relational databases with very carefully considered schemas that tell you how all the data relates to each other. And so they're kind of like these opposite ends of the continuum, the like in their like platonic ideals. In between is the data lake house, which mixes these two things together in one piece of technology. And this is one of the things that like Databricks, one of the big sort of like data technology providers in the ML space, is like most famous for pioneering that like marketing term and also the like technology underneath it to make that like a good user experience with like good, like high scalability, high performance, extensibility, reliability, etc. Okay. So the other piece about these like ETL workloads is because sources can like something can be the source of one job and the target of another job. So the output of one can become the input to another, just like as we pass tensors through our PyTorch modules, one layer's output is another layer's input. We also might want to take that structured data in the data warehouse and like restrict its access or like filter it down, refine it a little bit from this like unstructured gigantic warehouse that's like a Costco down into like a nice artisanal like candle store. I don't want to, if I'm on the candles team, I don't want to have to go to Costco and wander the entire place looking for candles every single time. I want to go to Candle Mart and find my candles. So data marts are kind of like highly structured team specific components built out of the data warehouse, like everything about sales, everything about marketing, everything about legal, all internal data that are images. I don't know. These kinds of things will go into these marts so that people who are working on specific teams don't have to go like to, again, create like a barrier between like all the complexity that might be there and you're in like a gigantic business with a huge application and what one person or one team can reasonably handle thinking about and handle the responsibility for. Data marts, in my impression is that this is like pretty deep into the weeds of like organizing a data system at a really big organization. So I would worry less about that piece than about the other ones that we've talked about, lakes, warehouses, and the like separation between operations and analytics. But it does come up every once in a while while you're talking about and thinking about machine learning. Okay. That was so great questions, Moise. We covered a lot of ground with just those few things.
Yeah, that was pretty awesome. Thanks for the overview.
Yeah, I do want to also caution folks, like I'm still learning a lot of this stuff. I've been like, I worked at Weights and Biases for 2 years and kind of like talked a lot with the folks working on the data infrastructure and talked with data engineers who wanted to like integrate their data infrastructure stuff with Weights and Biases. But this is not like I'm not an expert on this stuff. I don't build systems like this. So like I'm trying to give you my distillation of like those people's experiences and of like resources like Klepman's book and YouTube videos about how all these systems work. But since I'm not somebody who's thinking about and building these systems every single day, I would take some of the intuitions with a grain of salt. And if it's, if you're going to dive deeper into this stuff, you're definitely going to want to learn from the masters on this.
I just had a couple comments when I read this.
Mm-hmm.
I mean, first thing that came to mind is you need, unless you're Amazon or Google who provides the cloud storage service, you just can't keep everything. It doesn't make a business. It's not good business sense. So you gotta do some version control on the data, or you have to have some constraints on what you're gonna keep and not keep. So, like, for example, we're only gonna keep, if you're doing vision and you're taking pictures, we're only gonna cater to iPhone 12 plus 12 and up users. We're not gonna cater to anyone else or something. I mean, it seems like if you're just like a one-person show, you gotta pinpoint it. And then also that leads on to the other point where you can iterate on that data much quicker, and you constrain your further down the line the machine learning problem. So you're gonna need some experts who kind of make that engineering call on what we're gonna do at the start with the requirements.
Yeah, I think that's right. One bit about like choosing what to keep and what not to keep is storage without access is very, very cheap these days. And so the way this is reflected in the pricing of a lot of like cloud storage vendors. If you want to just write stuff to S3 or Google Cloud, that's like almost free. Like you can pretend that it's free, infinite storage. And it's the part where you want to like read and edit that where things start getting expensive. So it's like the Hotel California. But so what that means is you could kind of like hoover up all of this data that's coming in and throw it into something like a data lake where you aren't expending any effort to like read it, transform it, whatever. You're just throwing it up into buckets. And then if it becomes important later, then you spend the money to like pull it back down, transform it, etc. But I do think you're right that you wouldn't want to just look at all of that data and say every single one of these things I'm always going to want to pull it in and I'm always going to want to analyze it, because that's like once you get, there's just so much information produced by your system, like the running of your application, by the behavior of your users, that you like can't possibly actually like analyze all of it all of the time.
Right. And then when I was thinking about the constraint, then another thought came up is, what if your algorithm could, like, what if your algorithm, say you do online learning, your algorithm can adapt. So then the question is, what's the minimum amount of data you need? If your algorithm can adapt fast without needing a lot of data, then you don't necessarily need to keep a lot of data in the past. So I was just thinking, like, if you had a model that could adapt well, then that might reduce what you need to keep the version control with.
Yeah, I think the tricky bit there is you want your model to be recreatable, right? Like you want to be able to reproduce a model that somebody created. Otherwise, it's like far too easy to lose track of important information about that model and its behavior if it just ends up just being like a pile of weights stored in H5 file or whatever. And so that means you kind of want to keep the training data around in order to be able to like recreate the model. And then if you're doing continual learning, that means that the training data for a continually learning model like 6 months down the line is the original training data plus everything you ingested during that continual learning process. So I think a lot of people take this attitude of like, we've just got to hold on to everything, and then just treat it as like a cost of doing business or a cost of scaling that you have to hang on to all of that stuff. Even though you're right that in principle, like if your model's learning and you're confident that you don't need the data to train that model ever again, then you don't, strictly speaking, like need it in order to run the ML application. Okay, we've got about 5 minutes left. Any other pieces? I think the section about REST and RPC APIs is useful and interesting, just like as part of application design, just part of like system design in general. it doesn't even need to be a data intensive application that requires data engineering, but like using requests or RPCs is actually a nice way to kind of like organize a complex service, especially if it's composed of like multiple smaller microservices. This is not something I have a ton of experience with. I've done it just like once or twice, but it is a neat way to organize things. And if you use Fast API or like Django or whatever these like web frameworks in Python, then you might come across these ideas.
Can we get over to the data format section? I think it's towards the top.
Yeah.
Or so.
Yeah, data formats.
Yeah, if you go down to the table or down. So I do computer vision, and I want to go into video at one point, and that data set's just going to explode.
Yeah.
And it kind of, when your data letters start being the bottleneck, then it's the format that might determine like whether you go PyTorch or you go TensorFlow.
Yeah.
For example, like I've seen things where that TF record, moving all your video or sorry, pictures into TF record can really boost up your speed versus if you're in PyTorch. I don't know if there's like an equivalent of it yet, but just how your input data is formatted might push you into using one tool or the other for development. I was wondering if you had any experience with that.
Yeah, I would say that a lot of people are identifying the bottlenecks in PyTorch right now, and the data loader is quite frequently a bottleneck. And so people are trying to improve it, trying to like work around it. And I think I think you're spot on that like TensorFlow, because Google wanted to orient it towards enterprise scale production machine learning, the like TF records and some of the like TensorFlow data functionalities are like just a lot more performant than the stuff in PyTorch. So I think all of that is correct. There has been a lot of movement in the PyTorch world. I think it's unwise to bet against PyTorch just because of the strength of the like open source community around it. So FFCV was like a library that came out recently where some people were just like, God damn it, I'm tired of waiting on PyTorch data loaders. We're gonna write our own thing from scratch for computer vision, and that's like very fast. Maybe it's a recent library, and you'd want to check very carefully before you bet on it for a like scaled production use case, but it's still new and unstable. PyTorch video from Fair, nice, yeah. So it's cool to see that Fair is putting out their own libraries on it. Like there's also Torch Data. They're trying to like heavily refactor basically because the data loaders had too much functionality in them, and so with this newly stable Torch Data library, they're trying a heavy refactor to try and make it easier to make separate pieces that then become really performant on their own. Yeah. I think there was one other piece that I wanted to talk about. I mentioned FFCV, TF records, why we ended up in this situation, and Torch data.
I guess there's also a push for people to, at least for Vision, they're pushing the data loaders trying to do this transformations on GPU now instead of CPUs.
That's exactly what, thank you. That's exactly what I meant to mention. So like now, if you really reach the the highest heights of deep learning oriented data engineering, you need people have these like specialized systems where data can be fed basically directly into the GPU from like another machine even. And they have this like data specifically, they have like memory, like disk type memory directly associated with the GPU that the CPU doesn't go through. I think this is the NVMe. Oh man, yes, this is further than I've ever gone, so I don't recall directly. But you basically need specialized software, like your GPU oriented data loaders that like run operations on GPUs, and then you also maybe like need some sort of specialized hardware to make sure that process runs quick. But yeah, that is another way around it. And I think if you're looking at video, because now with video we've got height, width, channel, and time, you've now blown your tensors up by another dimension on top of everything else. And so you might need to like reach down, reach for these like furthest heights of the data engineering stack.
That's about right.
Got it. Yeah, that's I will say though, that's like a little bit closer to like this data engineering chapter is like a lot more oriented to everything up until the point where the data starts going into your model. Like because we were just like, 5-10 minutes ago, we were just talking about like operational databases versus the databases in your data warehouse and your data lake. Like all of that stuff is like very much so upstream of tensors being read from disks in order to pass through models. So like that's I would say that's not like strictly speaking within the remit of this chapter. The like how things are stored for directly for ingestion into your models. That's maybe like for what you do with the data in the data warehouse before you run your training job. All right, I think we're at 10 o'clock in Pacific time, so 1 hour in. And so I'll stick around for a minute or two. Folks want to discuss other things around the reading group or around other stuff with ML in production. But that's the end of our discussion of chapter 2. Starting with chapter 3, we're getting much closer to the machine learning, a little bit more detail. Chapter 3 is on training data, and the link is up on the Notion doc, and I'll be posting it in the Discord as well. Make sure to read it by next week so we can talk about it.
Thank you.